blockchain and DHT-based lookup system aiming for alternative DNS. 中京 University, Kazuma Matsuoka and Tsunehiko Suzuki. In this paper, we propose a lookup system using blockchain and DHT. The use of blockchain guarantees the integrity of stored data, and the use of DHT stores data among participating node distributed tree and provides a function that can retrieve and propagate any data efficiently. A general blockchain is modeled with a stack of at least 4 protocol layers: network, consensus, storage, and views. We adapted using column layer as network layer of our system. All nodes, transactions, and blocks are inserted as in the column layer overlay network. To enable all nodes to participate in mining process, it is necessary to propagate transactions and blocks to all nodes. So we use the cast that any node can propagate data to all nodes efficiently. Suppose that a node propagates a transaction using cast. Circles at the bottom of the binary tree represent nodes. In this example, there are 60 nodes. First, the node with the leftmost node, whose ID is 1111, sends data. Each list of k buckets of this node contains nodes enclosed by dotted line B0 to B3 in this figure. The node selects one node from each list of its k buckets randomly, numbered 1, and sends a transaction to that node. The recipient node computes the distance to that node, distance to the sender node, and selects one node from each list of its k buckets closer than that distance and sends the transaction. In this example, the leftmost node contains B3- of 0010's k buckets, so this recipient node relays the transaction to B0, B1-, or B0-, B1-, and B2- nodes. By operating this procedure iteratively, the transaction is propagated to all nodes. And we adapted proof of work as a consensus algorithm. Then we describe the design of transaction and block. Transaction contains key value, hash, owner, public key, signature, and block. Key values are contents to store. Hash is the hash value of the key and indicates which node holds this transaction. And owner is the ID of a node that issued this transaction. Public key and signatures. A public key is a public key that owner has, and other node can verify this signature. A block is the hash value of a block including this transaction. And this is a null value when the transaction is issued because it is not yet in the block. And the block contains the height, owner, nonce, previous hash, and transactions. Height is the order of the block. Nonce is the number that proves the correctness of the block. A previous hash is the hash value of a block before this one. Hash means the hash value of this block. So each review a previous hash of next block. The transactions are a list of transactions included in the block. We estimated the amount of data that each node will store. Suppose the amount of data of one transaction to be 1,500 bytes. So the total amount of blocks mined in 1 year is about 47,304 megabytes. It is essential to store any data to multiple nodes, for all nodes are not always active. And the number of recipients of a transaction and the block represents X and Y respectively. And the large N is total nodes in the network. the amount of data each node will hold as shown in left below equation, and the result of substituting the equation shows in the below right table. When a node stores that key value data in the network, it issues a transaction using that data. The transaction is broadcasted to share at all nodes in the network. If the transaction is legitimate, it will eventually be included in the block. And the owner node, which confirms that the transaction is included in the block, stores the transaction to some nodes that seem close to the hash value of the key to be able to retrieve from other node. When the node executes lookup at any data associated with key, first the query node selects some nodes close to key from its key bucket and sends find value message. If a recipient node has a transaction whose hash value is the same, it returns the transaction as an answer. If the query node got the transaction, it picks out a hash value of a block from the transaction. Then it sends a find block message to some nodes close to block to verify if the block really contains that transaction. Namely, our proposed system requires two steps to retrieve a value associated with the key. Moreover, this mechanism contributes to our desired name resolution system. We show the results of a simulation of our proposed lookup system. In this simulation, we measure the query time to retrieve any data and the success rate of retrieval while changing two parameters. First, we prepare some nodes in the virtual network and distribute a routing table to each node. These routing tables are different among each node and changed for each simulation. Next, 10 transactions are issued by nodes, and then one block is mined by a node. After that, we execute a retrieval query from all nodes and measure the query time. When considering the existence of offline nodes, we send a message to nodes to be offline before starting the measurement. We report the results of measurement. Upper right graph shows how the query time varies with the ratio of offline nodes. It can be seen that the query time increases as the number of nodes sending queries increases as the percentage of offline nodes increases. And below right graph shows the change in query time as the number of nodes increases. It can be seen that the query time increases as the number of nodes increases, regardless of the ratio of offline nodes, but at some times it decreases. Next is success rate. If all nodes storing specific content are offline, all nodes cannot retrieve that data. The probability P1 that this case will occur can be calculated from the number of offline nodes. The lookup of specific data succeeds unless all nodes that store it are offline. So the probability P2 can be shown like below formula. The result of substituting some values into P2 is shown in upper right graph. It can be seen that the success rate decreases when the ratio of offline nodes exceeds 30%, but even if the ratio is 50%, the success rate exceeds 99%. And below right graph shows that the change in success rate with the change in the number of nodes stored in the same data. If the number of nodes that store the same data is small, the success rate of the lookup to any data will be significantly reduced when the ratio of offline nodes increases. We talk about comparison of our proposed system and DNS. In DNS, a full-service resolver of DNS executes name resolving, and if it resolves an n-level domain name, it usually requires order n queries. On the other hand, in our system, if a key value data is stored at only one node, the expected value of lookup the node required is order 2 log 2n. Log n is the number of total nodes in the network. Because such scope is halved per query during iterative lookups at cadm layer, and our system requires 2 lookups to retrieve a value. But the expected value of each lookup decreases as the number of nodes storing the same data increases. In this paper, we described our proposed lookup system using DHT and blockchain techniques, and reported the results of measuring how the query time required for lookups any data changes depending on the network size and the ratio of line. The results of simulation showed that the query time increases with the number of nodes, but further investigation is needed to show that it changes logarithmically. In our system, 2 lookups are required for retrieval for any data completely, and the success rate of any retrieval is almost 100% in the environment with no malicious nodes. That's all. Thank you for listening.